given phi x, how do I get the strain in the wall of the shaft gamma? This is what we did in axial loading. It was very simple. The strain was simply equal to du dx and was uniform across the cross-section. Well, in torsion, things are going to be slightly more complicated. So we're going to ease your way there. So so this is step 1. And by the way, these things are called kinematic assumptions. These guys here are called the kinematic assumptions, that the cross-section stay flat and rotate rigidly by phi of x. Let's call them Ka, kinematic assumption. And this is what was our first step into doing torsion. First, we figure out what are the kinematics of the deformation. OK, the second step that we're going to do is we want to figure out how is gamma related to your phi of x. That's the relationship that we want. And because we're going to just ease you there, we're going to do a 2a first, which is this relationship for thin wall shaft. OK? So we said that if this is section x, this one is phi of x. Let's go a little further along by a distance dx, and let's take another slice. And now here, this rotation at x plus dx is going to be what? I'm trying to wake you up with easy questions. Thank you for waking up. That is phi of x plus dx. So let's take a nice saw, zip, 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 cut off this part, zip, 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 cut off this part, and then let's just draw this little section here of length dx. OK? So let's draw it up. I have, and we're going to do thin wall shaft. So we imagine that if I cut that, I only have a little thing like that. And so now this length here is dx from here to here. This, at x, the line there had already rotated by a certain amount phi, see, I keep putting x, phi of x. This is where the line is. OK? The line at x plus dx is not exactly straight, because if it was straight, it means the whole segment rotated rigidly, right? But this line here instead is rotated a little more. Maybe it's rotated up to here. So this here is phi of x plus dx. So now that line has an angle there. And this angle here of the line is our shear strain gamma in that little section dx. You see? It's the same as what we did over there, only there our length was L. We were taking the whole shaft. And here, we are taking a little segment of the shaft. And the line has rotated already all the way here at x. And at x plus dx has rotated just a little more, phi of x plus dx. Geometry still tells me the same answer. Geometry still tells me that gamma at x and radius r, because now we're doing this at everything is a radius r, is a thin wall vessel, is a thin wall shaft of radius r and thickness t. Gamma of x and r is going to be the same as that one. Remember how did we obtain this thing? It's going to be the rotation at the top minus, so it's going to be this segment divided by this segment. That's going to be the angle gamma. So this segment here is r times phi of x plus dx minus phi of x. This is how long this segment is, because it's the radius times this angle here. This angle here, up to here is phi of x. This is phi of x plus dx. So this angle here is the difference between phi of x plus dx minus phi of x. This angle here is this. if I multiply by the radius, I get this length. If I divide this length by the height, the x, I get this angle here. Okay? This divided by this gives me this angle. This length here divided by this length here gives me the angle. Okay? And this length is that part there. So this thing is the phi dx. So this means that gamma at radius r, position x, is equal to r times the d phi dx at x. All right? Brilliant. Notice that gamma depends on where you are. If I give you how much is d phi dx, I'm going to have bigger gamma for that d phi dx if my shaft had a bigger radius. See, it depends on r. Okay, so now we did a thin wall shaft. Now what we're going to do is a solid shaft. So what I want you to think of to make a solid shaft. So the solid shaft, now we do not have anymore the thin walls, so we're going to have, actually let me make it big because I'm going to use this picture a lot. So we graduate from 2a to full number 2, which is the relationship between gamma and phi in general for the axisymmetric shaft. So let's make a nice cross-section so that we can make nice drawings. So this is the whole cross-section of the shaft. And the outer radius of the shaft is still r. Now what I want you to imagine is that this shaft is like a leak. Did you ever see a leak? Did you ever cut up a leak? Do you know what a leak is? Okay, a problem with science here. A leek is like an onion, but it's like a cylindrical onion. They're like white and they have green leaves and they are fundamental to make potato soup. You cannot make potato soup without a good leek. Okay, they're totally cool. If you've never seen one, you have to do it. Like if you cut it up and you open, a leek is like an onion but cylindrical, so it's made of all these layers. Totally cool white layers. Nice and even.
So this is for solid stuff? So that was thin wall.
Yes. So I want you to imagine that this solid shaft is like a leek made of all these layers, all attached together. Okay, they're not free to slide with respect to each other. They're all layers like in an onion, and that's the way you think of the shaft. Okay, but it's solid. I just do like this for convenience. Okay, so and this is still my section between x and x plus dx. So that has not changed. So this is x plus dx. The outer radius is r, but then the whole thing is filled, is solid. So remember that this was where I was at x. So this was my phi of x. And this is where I am. So this is where this line is. And at x plus dx, I'm here. So this thing here is phi of x plus dx. And this line here is still gamma at r, at big R, sorry.
Wait, what is x?
What is x?
Yeah, the arrow.
Oh, it just tells me this is the section at x. I'm kind of taking this thing and put it like that. So this is the section that if I'm now vertical, so my x-axis comes from the bottom.
So you cut at x and cut at dx.
I'm cutting at x and I'm cutting at x plus dx. So that's still my slice through the shaft, you see? I take this section, zip, zip, cut it, turn it upside down, look at it, I'm like, oh my God, it's a leak. Okay? All right. So this gamma here, the shear strain in the wall here at R, nothing has changed from what we did down here. this was the shear at the outer radius r, right? But now I go with a knife, zip, 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 and I cut. I cut away some layers. Say that I cut away these outer 2 layers so that I stop now at r, a small r. I cut away the outer layer and I expose the middle of my leak, of my shaft. So the middle of my shaft now, it's at the same place, so I'm still like here. But now only the inside is visible. The height is still the same. But now I am at the radius r. Okay? You see? And I also come inside and I grab everything inside that layer. Okay? So I also take away everything that was inside the little layer. Like that. So I only leave a thin layer of thickness dr. Okay? So I went there and I pulled out, I took away the outside, I took away the inside, and I only have a small layer of radius r and thickness dr. Okay? Okay. So what is the magic of our kinematic assumption? The magic of our kinematic assumption is that the whole surface here had rotated like that. So if there was a line that I painted here, the whole line now is rotated by the same amount here. You see? So if on this particular layer, how much this layer rotated here, from here to here, this is still phi of x plus dx minus phi of x. Nothing has changed. So that angle there is still phi of x plus dx minus phi of x. This angle. But now, this segment here, that is how much I rotated in distance, this is an ugly line. This segment here, that is how much I rotated in distance, is this angle multiplied by the smaller radius. I have r that multiplies that. That gives me this segment here. So this angle here, which is now a gamma at small r, this angle here, I can obtain it as this distance divided by the same dx. This dx does not change. It's still my dx. Nothing changed. So you can imagine that out here, where you have a big radius, for the same d phi dx, you get a very large gamma. Then if you keep going inside, 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 you see this thing gets smaller and smaller and smaller as you get inside. So if you were to draw the angle is big, then a little smaller, then a little smaller, then a little smaller. Your gamma of r depends on r. So this is r d phi dx. You see, this one is a function of x. But then the gamma depends not just on x through d phi dx, it also depends on how far you are from the axis of the shaft. You see, your gamma is not constant over the cross section. This is a major change from axial loading. Okay, this makes your life a little more complicated than it was in axial loading. Because gamma now, gamma depends on the radius and x. We see that the gamma is going to be bigger at the biggest radius, so right? When you have a maximum of gamma at r equal r on the outside of your shaft, at the outside wall of the shaft. So your maximum gamma is at the outside of the shaft, but you're going to have gamma at every radius, and it's going to be smaller as you get to the center. So we got that, right? Now we know what is the relationship between gamma and du dx. the relationship is that our gamma is not just a gamma of x, like epsilon a was, is a gamma of x, but also of r, and is equal to d phi dx, similar to the du dx, but times r. Okay? Major difference. Okay? Okay. Let's see what else. Oh, one thing that I forgot. Okay, so see this gamma is the phi dx times r. In the case of this special shaft in which everything is uniform, so your d phi dx is constant. If I were to plot phi of x for this shaft over here, I would find that my phi of x for this shaft looks like that. It's just d phi dx is constant. And so because this one is my angle of twist phi, because it's phi of L minus phi of 0, then in this special case, the phi dx becomes phi over L. You see, because d phi dx is constant. Right? So this relationship here is the same as this relationship here for the special case in which d phi dx is constant. So this is constant d phi dx. The slope of this thing is phi over L. Okay? So this thing has that as a very special case. The same way as in axial loading, you can write epsilon equal to delta over L instead of writing du dx if everything is uniform along the length of the shaft.